So I want to use this last set of examples again for two purposes. I want to use it first to talk about how to think about the relationship between an equation between two variables, x and y, and what its graph looks like. And in particular, equations that are linear, meaning that they don't contain any higher powers of x and y other than the first power. Right? So we're not going to get x squareds or any of that kind of stuff. So that's the first object. And then the second objective is to talk about how to solve a system of two such equations, to find a common solution to two linear equations. And that'll be our overview of this last circle of topics. So I want to start in this example not looking at both of these equations at the same time, but just looking at the first one, y equals negative 2x plus 1. And thinking about how to relate our understanding of that as an equation with our understanding of what a picture of its graph might look like, and then a numerical, a data-driven understanding of what the relationship between x and y that this equation suggests actually means. So to start that out, so the first thing we can do with any equation in two variables to get a better understanding about what the relationship between those two variables is that equation suggests is to come up with some data points. In other words, come up with some values of x. And these can be anything we want to. So we're just going to pick some numbers and we're going to put them in there for x. And then use the equation to figure out what values of y are related to those x's. So for example, in the equation y equals negative 2x plus 1, suppose that I chose x to be 0. Then what would that tell me about y? If I plug a 0 in here for x, negative 2 times 0 is going to give me 0, plus 1 is going to give me 1. And so if x were 0, then that would mean that y would have to be 1. So if x is equal to 0, according to the equation, then y is equal to 1. I can also choose other values for x. Let's say I chose x to be 3 instead. If I choose x to be 3, then negative 2 times 3, negative 6, plus 1 gives me negative 5 for y. We'll do maybe a couple more here. If I chose x to be negative 2, then negative 2 times negative 2 is positive 4, plus 1 is going to give me positive 5. So that's going to give me a positive 5 for y. So at least for this relationship, every different value of x that I choose is going to give me a different value for y. But the more of them that I choose, and then plot the corresponding ordered pairs on this coordinate chart, so for example, the point 3 comma negative 5, I plot here by going from the origin out 3 units in the x direction, horizontally, and then 5 units down in the y direction. There's the point, negative 3, negative 5. So the more of those points that I plot, the clearer that a picture emerges that all of the xy pairs that satisfy this relationship all seem to lie upon a common straight line. That line. So that gives me a clue that this kind of equation, y equals negative 2x plus 1, its graph describes a straight line in Cartesian coordinates. So then the question is, what can that line, what does a picture tell us about the form of this algebraic equation? Or conversely, sort of what does this data tell us about the form of this equation? First of all, the way that this equation is written follows a familiar form. Y equals negative 2x plus 1. It follows this template, y equals mx plus b. I'm going to kind of write those in here. Y equals mx plus b, which anybody who's had algebra recently will probably, that'll ring a very well-rung bell in your mind. In that template, what does m, or let's start with b. What does b stand for? From our example, we observe that in our example, b is equal to 1. So then my question is, what feature of this line corresponds to that number 1? Where do I find that number 1 in this picture?
0.
Yeah, it's right here. It's the y-coordinate of this point. So this point right here hits at 1 on the y-axis. Or if we were writing both coordinates of that point, it would be 0, comma 1. It hits the y-axis. That's what makes this what we call the y-intercept of the equation. So in the y equals mx plus b template, b is the y-coordinate of the y-intercept. So that's why this line crosses the y-axis at 1, because 1 plays the role of my b. That one's easy to interpret. I mean, it's quick. Interpreting a y-intercept is a much easier endeavor. M, on the other hand, this is the one that gives people fits, but good fits. These are important fits to have in an algebra class, because this M is a concept, not just a letter, not just a number. It's a concept that's going to follow you through our course into pre-calculus, and then it becomes probably the most important concept in calculus when you get there. What does this M stand for? In our example, it's -2. But what is that -2? How is that number, -2, reflected in our picture? Well, that's close. So if we look at the X-intercept, that's the place where this line crosses the x-axis. So on the x-axis, the number 2 is actually out here. So it's away from my line. So this -2. -2 would be over here. So -2 doesn't seem to represent the x-intercept of my line. It looks like the x-intercept of my line is somewhere between 0 and 1. So it's not the number -2. So we have to somehow look to see where, maybe we can look in the data, in the table over here at the right real quickly, to see if the number -2 shows up there anywhere. Well, it shows up as one of our x-coordinates, but then it's paired with a 5, which doesn't seem to have any correlation with the parameters in my equation. So instead, we have to look somewhere else. So here's where we look to discover what that -2 actually is. I can find that -2 by looking at these two y values and observing that the relationship between these two y values is that to get from one of them to the next one, I'm subtracting 2. Put another way, if I look at these 2 points on my graph, that's this point and that point, the difference in the y-coordinates between those 2 points is that the second one is 2 down from the first one, right? Because the y-coordinate here was -1, the y-coordinate here was -3, and that's a difference of -2. But notice that that would only make sense if I chose these 2 particular points. If I chose 2 other points, let's say I chose my first 2 points, now to go from 0,3 to 3, -5, sorry, 0,1 to 3, -5, that's going from this point all the way over to that point. That's a much bigger drop in y-coordinates, right? That's all the way 1, 2, 3, 4, 5, 6 units down. So it's not just as simple as a difference in y's, but if we look at how the x's of those coordinates are related, we do see a pattern come up. +1, +3. Right? The reason that these y-coordinates dropped by 2, but these y-coordinates dropped by much more, they dropped by 6, was because there was a bigger change in the x-coordinates between these 2 points than between those 2 points. So where does the number -2 show up in a way that's the same for this pair of points as it is for this pair of points? It shows up as the ratio, the result of dividing this number by that number. If I divide this -2 by this 1, I get, what's -2 divided by 1? I get -2. But likewise, if I divide this -6 by this +3, what do I get? Also -2. So that's the sense in which both of those pairs of points that I chose are telling the same story. That -2 is a measurement somehow of the, let's call it the angle of this line. It tells me that this line is decreasing as it goes from left to right, and the rate at which it is decreasing is incorporated by this number -2. It's the ratio of the differences in the y-coordinates to the differences in the x-coordinates. We call that the slope of our line. And so we found the slope of our line, first by looking at the equation and seeing that it played the role of the m, right? But more to the point, pun possibly intended, we can find the slope of a line just by selecting any 2 of its points and doing the work that we did over here in the data table. By measuring the difference in the y-coordinates and the difference in the x-coordinates, and then dividing the former by the latter. Let's choose another different pair of points and do that calculation one more time, just to bring another familiar formula into the mix that does in formula fashion what we just sort of did in talkie fashion a minute ago. Let's say I want to find the slope of the line that joins these 2 points. Well, I can do that by subtracting the y-coordinates. Often that's written as y2 minus y1. Subtracting the x-coordinates, x2 minus x1, and dividing the results. So, if I substitute in the y2 and the y1, that's going to be negative 1 minus 5. So y2, y1, second y-coordinate, first y-coordinate. Do the same thing for the x's, second x-coordinate, first x-coordinate, 1 minus negative 2. And then simplify. But negative 1 minus 5 is negative 6. 1 minus negative 2 is the same as 1 plus positive 2. It's positive 3. Divide it out. Sure enough, that pair of points also gives me negative 2 for my slope. So the whole point of doing this work is to translate between an equation for a line and any 2 points on that line. What we need is to find the slope of the line that joins those 2 points by doing this kind of calculation, subtracting the y-coordinates, subtracting the corresponding x-coordinates, and dividing. And then we can fill in the slope on our template. Then all we have to do is find the y-intercept, which we can do by using the coordinates of any of our points, or if we happen to know what the y-intercept is, because we knew 0, 1 was on our line, then we know that 1 plays the role of that b.